We've talked a good amount so far about electrostatics, which is really dealing with charges that are not moving, that are stationary, hence the static part. We're now going to start looking at moving charges, and we'll be talking a lot about batteries and other sources of moving charge. And so we see here one type of battery, kind of looks like a car battery. There's a negative side, there's a positive side to it. And these lines going around here are actually the electric field, which is something we didn't talk about. But the important part is that there's an excess of electrons on the negative side, and they are attracted to this part on the positive side. So what ends up happening with those two sides, right? We talked about how there's one positive, one negative. Those excess of electrons on the negative side want to go to the positive side. Okay, they want to travel from the negative side to the positive side. The more formal way of saying this is that there is a potential difference between the two sides, and we'll talk in a little bit about what that really means. Okay, but for now, the key is that those electrons on the negative side of the battery or on the negative side of an outlet, if we're talking about an electrical outlet, want to go to the positive side. Here's the key, though, is we need a complete circuit. We need a pathway that allows the electrons to go from that negative side to the positive side. And so you're going to see in all these problems when we build a circuit, we're going to simply create a path for the electrons to travel from that negative side to the positive side, and in the process do something that we want by flowing through a light bulb or some other object. We're going to go ahead and talk about a few of the terms that we use to describe circuits. And the first is a term that we introduced on the last slide, potential difference. So potential difference is a way that we rate batteries and rate outlets, right? You have a 9-volt battery, you have a 1.5-volt battery, which is an A or a C. You have a 120-volt outlet. You might have certain appliances in your house operate on a 240-volt outlet. That potential difference, okay, which is measured in volts, is really a rating of how much energy the electrons have. Okay, what it actually represents is the energy per charge, but we say that it's just the energy because electrons all have the same charge. So the electrons in a 9-volt battery are going to have more energy per charge and therefore more energy than the electrons in a 1.5-volt battery. All right. We will often call it voltage. Voltage is technically an improper term, but I use it all the time, and I'm not going to be a stickler about that. It's just an improper term for potential difference, and it comes from the unit for potential difference. So potential difference is joules per coulomb, which ends up being a volt. Okay, so 1 joule per coulomb is equivalent to a volt, and that's where that term voltage comes from. The other thing we want to talk about is how we go about measuring these quantities. So a voltage or a potential difference can be measured with a voltmeter or a multimeter, which is what we'll be using mainly, which measures a lot of different quantities related to circuits. So when we're using one of these devices to measure voltage, whether it's a multimeter or a voltmeter, there's a very specific way that we do it. And we're going to talk about that here. We'll obviously practice it in the lab, but it is an important concept that you need to know. So here we have a multimeter, but it would work the same way if it was a voltmeter. Both of them are going to have two probes basically coming out of them. Okay, one red, one black for positive and negative. That's not the important part, though. The important part, though, is how we actually use those probes to measure the voltage. So when we're measuring voltage, okay, we touch the two probes to either side of the object. We want to make contact with metal on either side of the object. And so we say that the multimeter is connected across the object or connected in parallel to the object, right? So this might be a light bulb, it might be a resistor, and a lot of this is going to make more sense when we practice it in class, but you need to know that we connect this multimeter or this voltmeter across the object. The next quantity we need to talk about is current. So current is the measure of the charge flowing through the circuit. All right. It represents the number of electrons. What it actually is the charge per second, the number of coulombs per second, but it does represent how many electrons we would have going through our circuit at any given time. Okay, and it's measured in units of amperes, which is just a capital A, but 1 ampere is equivalent to 1 coulomb per second. One other thing to keep in mind here is this relationship between voltage and current. Just because you have a high voltage does not mean you have a high current, and vice versa. Okay, so that is something to keep in mind, and we'll look at examples of this as we work through some of these problems. But having a high voltage means the electrons traveling through the circuit have a lot of energy. That doesn't necessarily mean that there are a lot of electrons, right? You could have a low current, so only a few electrons with a very, very high energy per electron, or vice versa. You could have a high current, meaning a lot of electrons, with a low voltage, meaning that each individual one does not have that much energy, okay? So they don't necessarily go up together. When we measure current, we're going to either measure it using an ammeter, which is a device that's exclusively for measuring current, just like a voltmeter was exclusively for measuring voltage, or we could use a multimeter. We talked about how that measures many different things. There is a difference, though, in terms of how we're going to measure it. And the key difference is, rather than with the voltmeter where we just touched each side of the object, with the ammeter, we actually take our circuit that would have been complete like this, and we're going to break that circuit, okay? We're actually going to disconnect the circuit temporarily and force the flow of electrons to go through our multimeter and then continue on around, okay? So we always are going to break the circuit and actually put the multimeter there to complete the circuit again, and it forces the electrons through the multimeter. We call this wiring in series. So whenever we're connecting a multimeter, we're going to connect it in series, just like we always connected a voltmeter in parallel. We do have a way of calculating our current based off of the charge. We said current was a measure of charge per time. So our equation is simply that current is the change in charge, or the amount of charge that passes by a given point in our circuit, divided by the time. Okay. Now, if we want to get our units properly, our charge needs to be in coulombs, our time needs to be in seconds, and that will give us a current in amperes, which is our standard unit. One thing to keep in mind here is that the charge of an electron is that fundamental charge, 1.6 times 10 to the negative 19th. That will sometimes come up in problems involving current. The next quantity we want to talk about is resistance. So any object, with the exception of superconductors that we're really not going to talk about, but almost any object is going to have some resistance to the flow of electrons through that object. And I know that's a terrible definition because we're using the word in the definition, but that's really what resistance is. It's the amount that an object resists or impedes the flow of electrons through it. Okay, we measure resistance in units of ohms. Which is just symbolized here by omega, all right, the Greek letter omega. And how much resistance we have is not something we're going to talk that much about, but it depends on the material of the object, depends on its shape, what is its cross-sectional area, what is its length, lots of things about its geometry and what it's made of. That's what really affects the resistance, but we're not really going to get into that too much this year. So to bring all of these quantities together, current, voltage, and resistance are three probably most important quantities in a circuit. We have Ohm's law, okay, which tells us that V equals IR, okay? The voltage or potential difference across any object in a circuit is equal to the current flowing through that object multiplied by the resistance of that object. All right. And so just as a quick recap of units and symbols, this V here represents the voltage. It's measured in volts. This I represents the current, measured in amps or amperes. And this R here represents the resistance, measured in ohms. Okay, I know it's a few new quantities and a few new units, so it can be a little bit tricky, but those are what those symbols represent. Let's go ahead and try a quick practice problem here. So a typical 120 volt circuit in your house can handle a maximum of 15 amps. First, we want to find the resistance, so we're going to use Ohm's law here, V equals IR. Our voltage across this circuit is 120 volts. Our current is 15 amps is what we're told, and we want to solve for the resistance. So we end up getting that our resistance here for this circuit is going to be 8, and it's measured in ohms, so 8 ohms. The second question, how much charge flows through the circuit in 1 minute? So I'm going to be thinking about my current, and I'm going to link that to my charge with my equation here for current, delta Q over T. So my current is 15 amps. I'm solving for the amount of charge here, and my time is 1 minute, which is 60 seconds. And we want it in seconds because an amp is a coulomb per second, not a coulomb per minute. And so when we solve for our charge, delta Q, we get 900 coulombs of charge is going to flow through that circuit in a minute. The last part just asks for how many electrons that would represent. Okay, so 900 coulombs of charge, how many electrons do we have? And this is really just a conversion thing. We know that an electron is 1.6 times 10 to the negative 19th coulombs is 1 electron. And so when we go and solve for that, we end up getting 5.625 times 10 to the 21st electrons are going to flow through that circuit in 1 minute, which is an incredible amount. But to put that in perspective a little bit, that's still about 1/100th of a mole. Not that you have a great sense of what a mole is, but you obviously talked about that a lot in chemistry class. One last quantity we're going to talk about for circuits is power, and power is actually something we talked about way back in our energy unit. Okay, power is just a measure of the energy or work per time. It matters a lot for circuits because appliances are typically rated based off of the power that they use. Okay, you might have a 100-watt light bulb, a 1200-watt microwave, whatever the case may be. The appliance is rated based off of the power consumed by that appliance. All right, and so that power really depends on the energy per electron and the number of electrons per second. All right, so if we think about this, power is voltage times current. Voltage is really the energy per electron, and current is really the number of electrons per second. And so when we multiply those together, the electron piece cancels out, and we get energy per second, which is equivalent to our power. And so that's where that equation comes from. So we will sometimes use this to link the voltage and current of a particular appliance to the amount of power consumed. So power is voltage times current. Power is going to be measured in watts. All right, that's the standard unit. Voltage, of course, is in volts, and current is in amps. All right, so for this practice problem here, we have a flashlight, uses a 6-volt battery, and has a resistance of 0.5 ohms. What is the power of the flashlight? Well, power is just voltage times current. So we're going to take our voltage here, 6 times our current, but unfortunately we don't know our current. So we need to solve for that, and we can do that using Ohm's law, V equals IR. So 6 volts equals our current times our resistance, 0.5. And we find that our current here is going to be 12 amps. So I can then substitute that into my power equation, and I find that the power consumed by this flashlight is going to be 72 watts. Now that I have that power, I can go ahead and find my energy, and I'm just going to do that by saying that power is work or change in energy over time. So that 72 watts is equal to the change in energy, which is what I'm solving for, divided by 30. So that means when I multiply this out, I get 2,160 joules of energy is going to be consumed in 30 seconds.